Hello, 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 hello. Today what we're going to do is we're going to compare two proportions. Here's our scenario. The Huckleberry Consortium surveyed a random sample of 75 students and a separate random sample of 60 adults. For the students, 72% reported owning a Snoop cat. For the adults, the result was 65%. Do the data provide convincing evidence of a difference in proportion between students and adults owning a Snoop cat? State appropriate hypothesis for a test to answer this question. Address all conditions and assumptions necessary to justify the test. Okay, well, the first thing we have to do is we have to recognize we are comparing two separate proportions here. The results from the students and the results from the adults about owning a Snoop cat. So the first thing we want to do is define our parameters. So let's say P1, that's going to equal the true proportion of students that own a Snoop cat. Okay, and then P2, that'll be the true proportion of adults that own a Snoop cat. Okay, so what are our hypotheses going to be? Well, what we're checking for to see is if there's a difference. So our null hypothesis is the assumption that there is no difference. So P1 is equal to P2, that they're the same essentially. Another way of writing that you might see would be P1 minus P2 is equal to 0, meaning the difference, they're the same number, subtracted they get 0. So now our alternative hypothesis is that P1 is not equal to P2. They didn't say anything about one being higher or lower in particular. They're just checking to be if it's different or not. Again, over here, another way of saying that would be P1 minus P2 does not equal 0. So there are our parameters and our hypotheses, our null and our alternative. So the next thing we want to do is we need to check our conditions and assumptions. So first thing we always end up checking for is randomness. And you'll notice right here we have a random sample. So I'm just going to put, quote, random sample, end quote. And that's my reason that it is random. Check. The next thing we need to check for is that the 10% condition isn't violated. So we're going to note that our first sample size is equal to, where is it? Right there, 75. Oops. Do it a little backwards. 75. And that is definitely less than 10% of all students. So that would mean there's more than 750 students to choose from out in the world, or from the population of interest. Now, N2, that was 60 adults, and again, that is definitely less than 10% of all adults. This pen is getting really tough to write like this. Okay, so that covers our 10% condition. So 10%, check. Go ahead and underline that so we see that those are separate. What's the third one? The third one is large counts, or expected counts, that we have at least 10 from each. So from our first survey, we had 75 and we expected 72% to be successful. That actually equals 54 students. And so then 75 times the complement, 28. That gives us 21 students. Going on to N2, we have 60, and that's 65% was success rate. So we multiply that out, we get 39. And then times the failure rate, 60 times 0.35, And there we get 21. All of these are greater than or equal to 10. So large counts, check. So from all of this, what that allows us to do is a two-proportion z-test. So if you were going to use this in your calculator, do this in your calculator, you would do this. But remember, since this is going to be all free response, you have to show your work. So doing it with the calculator would only be to double check yourself. So moving on, the next main thing we have to do now is do our calculations. So we need to get a z-score. So let's go find z. And remember what z is. Z is going to be our data value of interest, and in this case it's the difference. And so it's that difference of 72% and 65%. And so that's our data value of interest minus the mean. And what do we expect the mean to be? Well, our assumption is that the mean is no difference. There is no difference between them. So that's going to be 0. We're going to divide this by the standard error. But here's a thing we got to remember. Our combined standard error here, with the assumption that this is a hypothesis test, assumes that there's no error. So we have to go ahead and combine these two pieces together. So we're going to have this fraction plus this fraction, but we have to figure out a new p-value. Because what's p hat between 72 and 65 with the sample size of 75 and 60? That's what we have to figure out. We have to figure out p hat combined. And that's sometimes it's called pooled. So this is all because we're doing a hypothesis test. We assume there is no difference. So in this case, what we do, the success amount is 54 and 39. We're combining the successes. So 54 plus 39, and that's going to divide by the sample sizes, which are 75 and 60. So we go over here, 75 plus 60. Now I've calculated this out, and our new p hat is approximately, it's actually 0.688 repeating. So I can tell you it's exactly 0.688888888 repeats. So we're going to approximate that to 3 decimal places at 0.689. Because if 8 repeats, the next 8 would round that 9 on up. So that's the value that we actually think of as success. 0.689. The complement for that, 0.311. Divided by the sample size, 75. And we assume it's correct over here as well. So we stay with the same 0.689 multiplied by 0.311. And that's divided by its sample size of 60. So we end up with z equaling, oh gosh, where did we get to here? Z equals 0.872981 dotly dot dot dot. So we're going to round that. We're going to say z is approximately 0.87. And that's the value we're going to go look at our table, our z table with. Now before we do that, I want to draw out what's happening. So we got our standard normal curve here. And if it's standardized, right there the mean is 0. So our z is 0.87 above here. So notice one standard deviation would be about there, one standard deviation would be about there, blah, blah, blah. So let's take those back out. If we've got 0.87 here, and we look in the table, where's the value going to be? Right, it's going to be the value going that way, to the left. And we're really more interested in the value going this way, because that's the direction that we're interested in, the difference. And by the way, this is a two-tailed test, so we're going to end up also getting this side, which will be the exact same amount. That's why we'll just double our answer. So when we go look up 0.8 and then over to the column of 0.07 in our table, we end up finding a value of 0.8078, which means going this direction is the complement 0.1922. So that's our probability here. So let's put this all together now. Using our table, our p-value, we got our z from our table there. Our p-value is going to be approximately equal to twice, because we've got both of these sides here, twice the probability that z is greater than or equal to 0.87. That's the z value we checked right there. Okay? That's the probability that it's there. So we found that probability right here. But really, we're looking for it to be greater than that. So we're looking for that guy, which is why we're doing 2 times 0.1922. When we do that, we get our p-value at approximately 0.3827. 38.27%. If you use technology and you do a 2-proportion z-test, like we stated down here, you're going to end up with a p-value. I'm going to do that in orange. So with tech, your p-value is going to be 0.3844. Look how close that is. That's really, actually no, it's 0.3827, my bad. Looking in the wrong place, 3827. Nope, that's the one that we just got there using that. So, it's slightly different with tech. Oh, sorry, 3827 is the actual answer. Over here, 3844 is the answer that I should have written. I was looking at the wrong place, sorry. You got in red. That's 0.3844. And if you use technology to do it, you get 0.3827. Very, very close, essentially the same idea. Either way, the point of the matter is this. When we get down to it, with p-value equal to either of these guys here, we'll go with the 0.3844, and an alpha level of 0.05, which is our normal if we don't have a reason to do something different, we fail to reject the null. In other words, we do not find sufficient evidence to believe that the two groups own snoop cats at different rates. We have not found that evidence. Now, let's go ahead and do a confidence interval for the same question. Now, in a confidence interval, let me remind you, we looked the other day and saw the way that they talked about it was the sample statistic plus or minus the z-score times the standard error. Let me go ahead and write that out a little bit more specifically. So, p hat sub 1 minus p hat sub 2, that's our parameter of interest. That's our sample statistic, basically. We're going to add or subtract our z critical value from that, and we're going to multiply that by the standard error. Now that, remember, is the addition of these two variances. And remember back a couple months back when we talked about variances always add, even if you're doing a difference, finding their standard deviation, we always added it. So that's coming up again right here. So what are we going to have here? We're going to have p hat sub 1 I'm just going to go with the easy q hat sub 1 over the sample size n1. And over here, we're going to have p hat sub 2 times, not plus, times p hat, yeah, you back up, q hat, good catch. I know some of you were saying that in your head. Let's get rid of that plus and make that right there. Good catch, everybody. Q hat sub 2 divided by sample size of 2, n sub 2. So, what do we know? We know that the proportion of students was 72%. Proportion for adults was 65%. So that difference is our sample proportion. In other words, that's 0.07 plus or minus the z critical value. Now that's not going to change in either one of these, so I'm just going to write it here, 1.96. And then we're going to multiply that by this right here. Square root of each of these fractions. And so what did we have for p sub 1, p hat sub 1? That's the probability for students. That was 72%. So 0.72 times its complement, 0.28. Divided by its sample size, 75. Over here, with the adults, we had a p hat of 0.65, and that would make q hat 0.35. And the sample size was 60. Now I want to point out really quickly, back here, if we go back and look at our hypothesis test, that's not what we used here for our standard error. We had to use this pooled or combined value, which we ended up getting an answer right there that we used. That's because here we're assuming there's no difference, so we combine these values together right here to get this value for both. But in a confidence interval, we're not making the assumption, we're not doing a hypothesis, so there is no assumption of equality. So that's why they're being done separately here. Now, let's go ahead and calculate this out. This actually turns out to be 0.0805 approximately. Now, when I actually did this, I kept going with the answer in the calculator here because I know that this keeps going. So stick with me. That's why I also went out to 4 decimal places there. So when we go ahead and simplify that, put that in the calculator, I always like to do the minus first because that's going to give me the lower extremity here. With the rounded number here, we get negative 0.08778. And then go put the plus number in, we get 0.22778. So there's our confidence interval. We are 95% confident that the true proportion of difference between students and adults that own Snoop cats is between negative 8.8% and 22.8%. And is that consistent with what we got back here? Remember, back here, we failed to reject. We didn't find sufficient evidence that it was different, that there was no difference of 0. Well, if we go here, 0 is within this confidence interval. So because 0 is within that confidence interval, yes, it is consistent with that result. So I hope that helps out, folks. Have a good time with this. If you have any questions, I'll see you in video conference, and enjoy the rest of your day.